All right, good morning, everyone. Let's get started. So we have been working our way through understanding how we're changing cardiac output, just in case you forgot where we're going. So how do we change cardiac output? Why do we care? Because cardiac output is going to be a primary determinant of mean arterial pressure. Okay, so that's eventually why we're getting there. We had talked about end diastolic volume. That was dependent, so that was how much we fill the heart. So that was dictated by venous return. Oh, wow. There are places I shouldn't walk. Okay, I'm gonna stand right here. That's gonna be difficult. So I don't know why we're getting feedback today. Try to put it somewhere else. Maybe right here? Nope. Okay. And diastolic volume. So we had, that was depending on venous return, so how much volume we were returning to the heart. So we kind of held on to that for a minute because we got to work our way around the vascular system in order to understand veins, in order to understand how we're going to get volume back. Then we talked about end systolic volume, essentially contractility of the heart, right? And how we had some intrinsic controllers of that and some extrinsic controllers, okay? So intrinsic controllers were the Frank-Starling law of the heart, essentially the leg tension curve, this phenomenon where when we increase heart rate, we increase strength of contraction. Those are all things that the heart was just going to do. It's how it's built. It's just going to behave that way. Then we had extrinsic controllers, so things like sympathetic nervous system, parasympathetic nervous system, because we have direct innervation of the sympathetic and the parasympathetic nervous system into ventricular myocytes. Okay, this is separate from the SNS and the PNS innervation that we talked about into the nodal cells, right? The nodal cells controlled rate. Okay, SNS and PNS innervation into the ventricular myocytes themselves control strength of contraction. It's a muscle. Okay, we can't control rate with the muscle. We can only control force with the muscle. Okay, and then what else did we add on there? Because we have sympathetic nervous system control and we have that membrane receptor population sitting there, the beta adrenergic membrane receptor population, then we have hormonal control over it as well. Okay? Because we can get sympathetic nervous system stimulating the adrenal glands, releasing epinephrine and norepinephrine, circulates around, finds that same membrane receptor population, and will do exactly the same thing that the sympathetic nervous system did. Then we shook on a little bit of paracrine control because there are cells close by the myocytes that release products, and then the idea of afterload. That what is the pressure and the volume, or the volume and the pressure in the aorta, dictating how long we will be able to eject volume from the heart. Okay, if we take longer to overcome the pressure in the aorta to open that aortic valve, the less time we have to eject, right? So we will reduce our stroke volume, or we'll reduce our stroke volume there. Okay, and then we got to the third variable, heart rate. We've been to heart rate before, right? This is SNS and PNS innervation into the nodal cells, okay? So we've covered this already once, so this is just a repetition of that. And then because what we did add here was because we have that, got to have a beta adrenergic membrane receptor, or an adrenergic membrane receptor population because of the sympathetic nervous system released norepinephrine and it affected the nodal cell. Then the sympathetic nervous system can stimulate the adrenal glands to release epinephrine and norepinephrine. That released into the blood, it will circulate around and find that same membrane receptor population and do exactly the same thing. Okay, slightly different time scale. It takes a little time to circulate around in order to find that membrane receptor population. Okay, so really fast ways of changing heart rate and then a slower way. And by fast, we're talking milliseconds to seconds. And by slow, we're talking seconds to minutes. Okay? Okay, so when it comes to heart rate, though, we do know that, that'll be great. We do know that the relationship between cardiac output and heart rate was one where cardiac output equaled heart rate times stroke volume. So in this relationship, it would stand to reason that when heart rate goes up, cardiac output goes up, right? And that relationship, maybe if we were to plot it, might be linear, right? As heart rate increases, cardiac output increases. That's what this equation, or this relationship says. But there are some ways that I could make up or that I could think of where an increase in heart rate could actually decrease cardiac output. Okay, so for example, if I increase my heart rate like really fast, I'm actually going to decrease the time that I have for diastole, right? And diastole is the time that we fill the heart. And if I have less time to fill it, I have less volume, I have less preload, and I can only pump. I can't pump what I don't have. So I have less in there to pump, I'm going to have less in there to eject. So there is a possibility, like we can think of a scenario, right, where an increase in heart rate might actually cause a drop in cardiac output. Let's write that argument out. So if I had an increase in heart rate, if I have an increase in heart rate, we get a decrease in the duration of diastole. That is ridiculous. Keep it up here. Decrease in the duration of diastole, right? This is a decrease in filling time. There's nothing I can do with this. A decrease in filling time. All right, so if I fill the heart less, I've got less to pump. So this is essentially will result in a decrease in preload or a decrease in end diastolic volume. Okay. I feel like okay, we're going to take a 5-minute break. I'm going to call over to Teaching Support Services and get a new thingy. It's this thingy right here. Driving me nuts. Okay, so another mic is coming over. So let's persevere until that one gets here. All right, I'm going to leave it there, and I'm going to try not to walk. Okay. So we're talking about an increase in heart rate where we would have a decrease in the time of duration of diastole, decreased filling time, decreased preload, so a decreased end diastolic volume. All right, and based on that Frank Starling law of the heart, a decrease in end diastolic volume is going to be a decrease in contractility, decrease in stroke volume, right? Which is going to result in a decrease in cardiac output. Okay, so we could see where there might be a relationship between heart rate and cardiac output that is not positive. Okay, so we could see maybe that there was a negative influence of heart rate on cardiac output. And if we do go back to the original equation, yeah. So we're going to have to check that out. So the question was, is that only when the heart rate increases rapidly, so the rate of increase? So it might not actually be the rate of increase. We might actually see that it's the absolute amount, the absolute heart rate. So maybe this only happens at certain heart rates, like really high, right? But we're not sure, because all we know is we've got one relationship that makes sense, but then where it's positive, and another relationship where it seems to be negative. So essentially, we're just going to have to do the experiment. We're just going to have to check out what heart rate is, or pace the heart, and as we increase heart rate, what does cardiac output look like? Okay? So we'll show that graph in a minute. So there's instances where it looks like there is a positive relationship between heart rate and cardiac output, where there's negative relationship with heart rate and cardiac output. And also, if we think about heart rate, if we think about this relationship, if I were to increase heart rate, I increase my cardiac output, so I've just increased volume in my aorta, right? That is afterload. So I've increased afterload. I should actually then decrease my stroke volume, right? So we could see another scenario where we could make it up where there might be a negative effect of heart rate on cardiac output. So let's write that one out. So if I do have an increase in heart rate, and that leads to an increase in cardiac output, right, from my first relationship, this is going to lead to an increase in afterload. Okay, I've got that increase in afterload, so therefore I'm going to have a decrease in stroke volume, we would predict. And that would be true. And if I have a decrease in stroke volume, therefore I'm going to have a decrease in cardiac output. Okay? So the other thing we don't know is how important each of these are as an effect. Okay? And then we talked about if I increased heart rate, we had that staircase phenomenon. If I increase heart rate, I increase contractility. That was that staircase phenomenon. Increasing contractility would mean I've ejected more, so I've got a drop in end systolic volume, and that results in an increase in stroke volume and an increase in cardiac output. All right, so this looks like a positive effect of heart rate on cardiac output because it's so integrated. Oh, hello. Just hang on, we'll get switched out here. Okay, we'll try again. Okay, we'll try again. I'm not sure we actually fixed anything. I think the whole thing needs to go. There's less feedback though. That's pretty good. Okay, so we'll just try to keep it going. Try to be very quiet up here, which is not going to work. Okay, did I press go? We're going. Okay, right. So we have things that we can think about where we see heart rate might have a positive effect on cardiac output and heart rate will have a negative effect on cardiac output. So we just have to do the experiment, right? So we have to pace a heart, look at what its heart rate is, and look at what its cardiac output is. Okay, so essentially if we look at that relationship, let's say we look at heart rate in terms of beats per minute. Okay, and we're going like 50, 100, 150, 200, 250. Okay, And then we look at cardiac output in terms of percent, right? So let's plot it against 100% of what we could get. We will actually find a relationship that is not linear based on what we've already seen. We're going to go here and here. So it's going to look something like this. Possibly not as steep as all that, but okay, something where we come up to a plateau around 150 to 180. Before we start dropping. Okay, so we do get what looks like a relationship where there is a positive relationship between between heart rate and cardiac output at lower heart rates, right? So there is a spot here where the positives outweigh the negatives. There's a spot up top where the positives are equaling the negatives. And as we increase heart rate, there's a branch where the negatives outweigh the positives. Okay? So these relationships do exist and all have an impact. But now it all just depends on what heart rate actually is. So it does make sense, really, that at very high heart rates, we would have a decreased time for diastole, and we might impinge on filling and therefore impinge on stroke volume and cardiac output, right? And we do seem to be, so all of these things exist. They just exist at different, they have different importances depending on what heart rate actually is, okay? We usually optimize ourselves. Humans optimize themselves around 180 beats per minute. So myself, I'm not significantly trained. So if I were to run, probably not on my own volition, but let's say being chased by a bear, I could probably get my heart rate up to 120 beats per minute. Okay, that is not optimal for my cardiac output. When a human trains themselves though, so let's say they are running on a regular basis, then they will actually train their heart, or their system will train to lower the heart rate to be a maximum of 180 beats per minute. The system optimizes itself around cardiac output. So you don't train, the system does not get trained to increase heart rate, and then you train more and your heart rate goes higher, and you train more and your heart rate goes higher. Because at some point it's going to have a detrimental effect on cardiac output, right? So you'll find an elite athlete will be able to get their heart rate up to 180 beats per minute, but it won't go further, right? Because the system isn't optimized for that. Couch potatoes like myself, totally get myself up to 220. It's not great, especially when being chased by a bear, okay? So we do optimize, the system will optimize itself to be able to have a maximum of, on that plateau, to a maximum of about 180 beats per minute. Okay, so we don't, so trained folks don't dip themselves into this branch of the relationship. Okay, so all of those characteristics exist. It just depends on at what heart rate you're at. Okay, so the question up front, was it the rate at which your heart rate goes up which dictates it? And it's not exactly the rate at which it goes up, it's actually just the absolute heart rate that you're at, okay? Any questions around heart rate there? Things start to get complicated because things start to get very integrated, okay? But that makes it cool. Okay, so let's just recap. Let's recap where we've been. Okay, cardiac output. We've been thinking about cardiac, give yourself a little space here. Cardiac output was equaling heart rate times stroke volume, and then we busted out stroke volume to be end diastolic volume minus end systolic volume. Okay, and what we were thinking about is how do we change end diastolic volume, right? So we did talk a little bit about preload. And this was our volume in, volume coming back to that ventricle, and that'll be based on what the veins are doing, so we'll come back to that. We talked about end systolic volume, and we talked about how there were intrinsic controllers. We also talked about the sympathetic nervous system. So the intrinsic we're not going to put on here because the intrinsic is just going to happen, right? So if we think about the extrinsic effects, we talked about the sympathetic nervous system and how that had an effect on end systolic volume. It's that contractility. We talked about the parasympathetic nervous system and its effects. So innervation into the myocytes, change contractility, and because we have the sympathetic nervous system working through an adrenergic membrane receptor, we will find there, then we also have hormonal control over end systolic volume. We threw in a little bit of paracrine. That we're not going to change a whole lot during this because we actually know very little about it. We talked about how afterload would affect our ability to eject volume. And then we talked about heart rate. We talked about how the sympathetic nervous system could affect heart rate, how the parasympathetic nervous system could affect heart rate. And then because the sympathetic nervous system innervates and uses norepinephrine and an adrenergic membrane receptor, we have hormonal control over heart rate. We talked about how heart rate could change contractility, right? So that was that staircase phenomenon, increasing heart rate, increasing contractility. We just threw in the potential that heart rate can actually change end diastolic volume. Okay, we just thought about that relationship. So that was our filling time. Okay, and then when we start to build how everything is related and interrelated, we then have to start to ask ourselves, okay, are all of these inputs equal? Just like we did on the last heart rate, cardiac output example. Are all of these inputs equal, or is there a hierarchy of power of these inputs? And indeed, there is a hierarchy of power here. So there are more potent regulators of this system. Okay, they're not equally potent. There's not an equal gain in terms of changing cardiac output. So if we think of the most, or if we list the most potent regulators, of the system, the first, or on top of that list is nervous and hormonal regulation. Okay, so the nervous and hormonal regulation is the most potent way to change this system. The second most potent regulator is our issues that deal with volume. So volume regulation, so that's going to be like preload. And our least potent regulator of the three are things that deal with pressure. So for example, our afterload issue. Okay, so if you ever had to choose, if you were given two regulators and you had to choose which one had the most power over regulating the variable or cardiac output, then we would choose in that order. Okay, if we said what's most, I've got two things that impact afterload versus the sympathetic nervous system. you would absolutely, there would be a greater power of the sympathetic nervous system over afterload. Okay? Yeah. SNS, PNS, and hormonal all fall under number 1? Yes. Yeah, so staircase would be an intrinsic regulator, so that's just going to happen. Staircase, would we classify that as a, so if I had an increase in rate, an increase in contractility. Yeah, so it doesn't neatly fall under any category, really, in terms of filling time. So I would probably put filling time under a volume regulator. Right? Filling time is really affecting our preload, so I would probably place that there. Where would I put staircase? Heart rate. Intrinsically affects stroke volume. Yeah, these are just like extras, right? I think paracrine, so afterload would be the pressure regulation. Paracrine would probably fall number 4. I think that's just a matter of the amount of tissue being affected. Like when you think of paracrine, right? Like we talked about that endothelial cell layer on the inside of the heart. And so because endothelial cells lie in close proximity to ventricular myocytes, they might affect it. But it's really only the inner layer of the ventricular myocytes, right? It's not like the whole thickness of the thing. So I would probably drop that one down lower for sure. But I'm going to have to think about where staircase fits in. Staircase is a contractility issue, and contractility. Well, if I was going to put it anywhere, I'd put it there. Only because changing its contractility is going to change cardiac output. Intrinsic regulators are a bit difficult because they are just going to happen versus these extrinsic. So I would probably place it there. Definitely not as powerful as nervous or hormonal control. Yeah, it might be there or there. Not sure. I'd have to think about that one in terms of these categories, or whether there's actually a number 4, which would be other. But I don't know about that one. Yeah. Mm-hmm. Right, so the question is if we lose function of a more potent regulator, would a secondary regulator kind of pop up as being more important? I think the answer would be yes. If you lost it as a controller, then others would appear more powerful because you lost it as a controller. Yeah. So if you went in and you blocked the sympathetic nervous system, so do not try that at home. But if you went in and you put in a beta adrenergic blocker into the system, which we do, that's one of the ways that we help folks in heart failure. Okay, so it's a big hammer in order to try to fix a problem. But if you lose, so if you lose a hormonal regulation over a system, it's not that one would move up then to take its place. It would just, one would become more apparent in terms of effectiveness. Yeah. Okay, so that's kind of an overview of where we've been in terms of trying to control cardiac output. All right, and I just want to keep centering us on where we've been. So we have, if we go back to where we started all of this discussion, okay, we have been thinking about our tools, our effectors in terms of controlling mean arterial pressure. We've been focusing on the cardiac system. okay? And we've been focusing on the cardiac system in terms of cardiac output and diastolic volume and systolic volume heart rate. And then we connected those systems up with the coordinating center, right? So how does the coordinating center control those? Right, so just as again, backing us up as to where we've been talking a little bit about glands, right? So we have seen systems where the sympathetic nervous system stimulates the adrenal glands to release hormones to then affect our tools. Okay, so we've seen a little bit about the gland system. And now we need to move on then to think about the smooth muscle. Okay, so now we're going to head into, we've been thinking about the pumps. Now we need to head in to think about the pipes. Okay, so that's where we're headed next. So we're going to do the similar type of thing. We're going to look at the piece of tissue and how does it operate, and then we're going to connect it up with what controls it. And we're going to think about how that affects mean arterial pressure. Okay, so we're going to go through the same process, but we're going to think about those, we're going to think about the blood vessels, okay? So just an orientation as to where we are. And indeed, I'm just going to show this. We've been thinking about our pumps, and now we're going to start thinking about each of the pipes individually. We're going to look at our arteries, our aorta, resistance arterioles, capillaries, and veins. Okay, so that's where we're headed. Just to try to remember where we are in our big scheme of things. Okay, so we're thinking about our systemic vasculature now, okay? Essentially, where is all of this cardiac output that we've been talking about? Where's it going? It's flowing through the pipes, okay? So if we think about where is cardiac output going, and we are thinking about that left ventricle, right? So we're going to be focusing on the systemic system and not necessarily the pulmonary system at the moment. All right, so if you think about where it's headed, it's going through all of the different pipes that we just had up on that diagram. We're looking here at the diameter of the blood vessels that we're going through and what the pressure in those vessels are. Okay, and you can see our large arteries and our aorta would be right up here. Okay, this is aortic pressure, not action potential. Okay, so we've got our aortic pressure up here, and we talked about regulating that at around 100 millimeters of mercury. Okay. And then we get flow of that cardiac output from our aorta to our arteries, to our arterioles, into our capillaries, and into our veins. Okay, so that's what we had kind of planned out as our major pipe categories that we were going to look at. Really critical is what the pump did for us, right? And that was set the highest pressure in the system, because in order for us to get flow across this system, we're going to need a pressure gradient. Okay, so this gets us back to this. The flow is going to be dictated by a pressure gradient and will be inversely proportional to whatever resistance through the system is. Okay, so what aortic pressure gives us, what that 100 millimeters of mercury pressure gives us, is our P1. That's the highest pressure in the system, right? Then the only thing that's going to drive flow through the rest of the system is that pressure gradient. So there has to be a pressure drop across the entire system, or else you get no flow. Okay, so we start out at 100 millimeters of mercury. If we are going to get flow to the arterioles, through the capillaries, into the veins, every compartment, there has to be a pressure drop. If pressure goes high, there's no flow. The whole system stops. Okay, so the heart is setting, the pump is setting our highest pressure for us. Okay, that was the reason for the pump in the first place. Sets that highest pressure in the aorta, and then we got our lowest pressure over here in terms of our pipes in the veins. So we see venous pressure. it's going to be about 7 millimeters of mercury. Guyton will call this, he was actually the first person to measure mean arterial pressure, the author of the textbook for the course. So he coined the term mean circulatory filling pressure. So you'll see him speak of mean MCFP. So what is the pressure in the veins? That's kind of all, they're all synonyms up there. Mean circulatory filling pressure is 7 millimeters of mercury. Okay, but we don't just need to get blood back to the veins, do we? We need to get blood back to the right atria. Right, so can you guess what the pressure in the right atria is? Or the range it has to be in? Yeah, it's got to be below 7. We're not going to get flow into the right atria if the pressure in the right atria is 8. No flow, no return to the heart, end of story. Okay, so right atrial pressure is about 0 actually. But we'll return to that idea when we talk about the veins side of things. Okay, was there a question out there? Yeah. So what counts as a resistance vessel? So we talk about resistance, most of our resistance being able to be gained in what we call resistance arterioles, the resistance arterioles right before every vascular bed. Right, this is where the most resistance, right, can be affected in the system. The arteries, the aorta, large arteries, small arteries, they all have smooth muscle around them. They can constrict as well, right? So they can contribute to resistance, right? So that's why you'll see them here as resistance vessels, because they can change their diameter. The most potent ability to change diameter is right there. Okay, so that you can change diameter in the system for sure, but our most potent regulators of resistance are going to be our resistance arterioles. Okay, so the just a quick note as to how we're actually moving through the system in terms of the incredible divergence that's happening. And convergence in the system. So we get, when the system diverges on the arterial side to the capillaries, we have one aorta diverging into up to 100,000 arteries, 2.8 times 10 to the 6 arterioles, and 2.7 times 10 to the 9 capillaries. So huge increase in number as we go down this vascular tree. And large changes in diameter. So we go from one aorta, which is about 12 millimeters in radius, down to capillaries, which are about 4 microns. It's about the size of a red blood cell itself. Okay? So just to get a feel for what this system looks like, right? It's not just one set of tubes or one tube splits into 3 like my little stick cardiovascular diagram. Okay, we got one aorta, and eventually we go down into 2.7 times 10 to the 9 capillaries as we work through all of those 600 vascular beds. And then we converge into veins, so now we start to build the system back up in terms of diameter, so diameter is going to get larger, and the vessels will get fewer. So we get into 1 times 10 to the 7 venules, 500,000 veins, back to 2 vena cava, okay, the inferior and the superior. Okay, so we're going from something very big down to lots of things that are really small, back to a couple things that are really big. That's how the system is built. Okay? But each blood vessel compartment, they'll have different characteristics, obviously. I mean, based on like the size difference, we know that each of these compartments have different jobs: transport, resistance, exchange, and storage. They all have a vascular wall. The characteristics of this compartment would be dictated by the characteristics of the vascular wall, but they all have similar components. Okay, so let's look at the vascular wall components. So, I better write that down. So we are talking about blood vessels, each compartment will have different wall characteristics. They all have the same layers, but variations on the same layers. Okay? So the layers that we're going to talk about here all have variations on these layers. Okay, so if I'm thinking about a blood vessel, let's say this is this is a little piece of my blood vessel, and we were to take a look at what that wall looked like, okay, that's what this picture is. Okay, so we're looking at a cross-section of one of the walls, and the area that's right closely associated with the blood will work from the blood out. So this is the lumen of the vessel. So the lumen of the tube. So this is where we're going to have blood flow. We have that endothelial cell layer. That endothelial cell lines the entire system. We met it when we talked about the heart and paracrine. It's sitting on a basement membrane that's sitting on a layer of elastin and some connective tissue. Okay, so that's kind of the first layer, called the intima layer. The next layer as we move out is primarily where our smooth muscle resides. And we're going to find neurons in here, and primarily it'll be the sympathetic nervous system. Right, so from the outside, we've got the sympathetic nervous system neurons coming in to this this medial layer. And unlike skeletal muscle, when we saw skeletal muscle being controlled by a nerve, we had an alpha motor neuron. There was a motor end plate. There was one motor end plate per skeletal muscle fiber. So every muscle fiber had its own little connection with the nervous system. In smooth muscle, in blood vessels, there isn't necessarily the same architecture. We don't have a motor end plate per smooth muscle cell. Okay, basically, we have multiple places along the sympathetic nerve where a neurotransmitter can be released. So neurotransmitter floods the area. So we're not necessarily looking at a one-to-one connection here. We have the nerve coming in, releasing norepinephrine and flooding this area. Okay, so the architecture is a little bit different. And so the smooth muscle cell layer and the neurons, that's referred to as the medial layer. And then now again, continuing to work our way out, there is a layer that, that the neurons went through, the adventitial layer. There does seem to be release of product into this adventitial layer. So we do have neurons here. It's primarily the sympathetic nervous system. We have macrophages hang out here, fibroblasts. A lot of work has been done on the intimal layer and the medial layer, and now a lot of work is starting to crop up in this adventitial layer. It seems to be much more active than originally thought. There's all kinds of cells here releasing all kinds of products. So a lot of work being done. We don't know a lot about this adventitial layer, but a lot of work being done there. Okay, so what we mean then by all, like that, each vessel compartment that we've been talking about will have these layers and different, and that will make up the characteristics of that layer, okay? Except for capillaries, do not have all of these layers. Remember, we wanted to optimize that for exchange. So a capillary is only an intimal layer. So capillaries have these endothelial cell layer only. That endothelial cell layer does sit on a basement membrane. Okay. So we'll find capillaries are stripped off completely of all the other pieces and just really consist of an endothelial cell layer sitting on a basement membrane. That's it, because we want to optimize it for exchange. But the other layer, the arteries, arterioles, and venules have each of these, and the characteristics of each of these layers make up why the wall characteristic is different. Why is a vein really elastic is dictated by these layers and the characteristics in that vein. Why is the aorta much more rigid? Because of the characteristics here. Yeah. Yeah, so so you have nerves coming in from the adventitial side in through to the medial layer. So that's how the nerves enter the blood vessel, right? And then will be able to release, so they're not releasing hormones, right? They're releasing neurotransmitters. Hormones you're going to find hormones up here. Right, when we're thinking about compartments, hormones are out in the blood. So if we're going to find hormones, they're going to be out there. Right? When a nerve is releasing the product, it's a neurotransmitter. It's primarily the sympathetic nervous system. So it's going to be norepinephrine is what's released there. Epinephrine is the hormone, yeah. We don't know. Yeah, I mean, we're not sure what the relationship of the adventitial are and why they're there. We're not really sure. Not a lot of work has been done on what's going on in that adventitial there. Yeah. Mm. So the capillaries are only the endothelial cell layer in the basement membrane. So the capillaries will not have elastin and connective tissue. There might be a little bit of it there to try to keep integrity of the vessel wall, but it's not there in any great amount, right? Again, we want to strip it down so diffusion can happen unimpeded. We want that layer to be as thin as absolutely possible because we have to use diffusion as a tool, okay? All right, let's take a quick break and get back here at 9:30 to continue. All right, everyone, let's get back at it. So the nature of the wall of the vessel then is going to determine the behavior of the vessel. It is interesting that in order to understand the compartments, and knowing that the compartments were different, the first pass that physiologists tried to do was to look at the cross-section of the different vessels and see what is different about them. And you would think that if you had arteries that were resistance vessels, they'd have a lot more smooth muscle, right? That makes sense. And you would think that veins, which are really elastic, might have a lot more of the elastic components and less connective tissue, right? You would think that you could predict that. But it turns out that if you do a cross-section of any of these blood vessels, these bigger blood vessels, and you look at the constituents, you cannot predict what that wall characteristic is going to be like. So it is not true that arteries have more smooth muscle than veins. It is not true that veins have more of an elastin layer than arteries, right? So oddly enough, when we look at these components, we can't predict what the vessel is actually going to be like, what the characteristics are going to be like. So it really just means that we're looking kind of at the wrong things. We're not quite sure what the right things to look at are. But looking at the vessel wall itself, other than capillaries, has never really given any good feedback as to what the characteristics of that compartment are going to be like, or what that vessel is going to behave like. So we essentially just have to go in and look at how the compartment behaves, or look at how the blood vessel behaves, because we can't predict it based on what the cross-section of the wall looks like, which is weird. Anyway, so the nature of the wall is going to determine the behavior of the vessel. So if we look at pressure volume or volume pressure relationships with these different vessel types, so if we took out an artery and we were able to add volume to it, measure its pressure, add more volume to it, measure its pressure, add more volume to it, measure its pressure, we get this really, really steep relationship. So very small changes in volume result in very large changes in pressure. Okay, so these are our large arteries. Our aorta is up here as well. And the relationship that we see is very small changes in volume equal large changes in pressure. So it ends up being quite a rigid, stiff, non-compliant compartment. It's not stretching when we add volume. Okay? Very non-compliant compartment. So conversely, if we do the same experiment with the vein, if we were to add volume to a vein and check its pressure, and add more volume and check its pressure, we get a very different looking relationship where we can add liters of volume now. Okay, here we were adding milliliters, and adding a couple more milliliters and a couple more milliliters, a couple more milliliters, and getting massive changes in volume, or massive changes in pressure. On the venous side of things, you can add liters of volume and have very low pressure. And then I can add another 500 mils and get not a whole lot of change in pressure. And then add another liter and not get a whole lot of change in pressure. Right? This thing is like, like when you're filling up a water balloon. Right? The more you add, it just expands out, right? So the pressure doesn't build. So on the venous side, so these are our veins, they're very compliant, very elastic compartment. Where large changes in volume are going to result in small changes in pressure. A system where we have small changes in volume with large changes in pressure, like our arteries, right? That's a brilliant way to build a system for transport, for movement of something from A to B. We don't want volume to reside there. We want volume to move, right? So small changes in volume are going to be the large changes in pressure. Remember, arteries are on the high pressure side of things, right? And then we had this compartment where our venous compartment, where we talked about storage, where most of our volume will reside at any given time. Up to 65% of your blood volume will be on the venous side at any given time. Right, so we need a compartment that's very compliant that can manage that amount of volume without changing pressure. Right? Remember, we're on the low pressure side of things. If small changes in volume resulted in large changes in pressure, we would inhibit flow across the system, right? So it has to be built this way in order for us to be able to allow for flow to occur, okay? So we're dealing with the venous side. We can't mess with pressure too much, right? Small changes in pressure on the venous side will really affect flow, okay? So it all matches, which is great. So we've got an arterial side for transport, rigid, small changes in volume and large changes in pressure. Right? That's where we were putting our cardiac output, remember. So it's quite easy to change pressure in this compartment by having small changes in volume, small changes in stroke volume, small changes in cardiac output. And then a large compartment on our venous side, very elastic, hold lots of volume. Okay, but again, we have to just go do that experiment, because just cutting that wall in half and taking a look at the constituents of the vessel wall would never have told us this behavior. Okay? All right, so now let's start working our way around those compartments. So let's start looking at the aorta, and then we'll work our way to our resistance arterioles, then capillaries, and then pop into veins for a little bit. Okay, so let's work our way around there. We'll start with the aorta or the arterial compartment. So aorta, large arteries, small arteries, this type of thing. But let's look right at the aorta itself, right? Because that's where we were when we were messing with the ventricle, the left ventricle, and we're looking at pressure volume relationships. We were thinking a fair amount about that aortic volume and that aortic pressure, because that's our afterload, right? So that's where we've been thinking about the aorta already. So if we think about the pressure or the pressures that we'll see over time in that aorta, that is being dictated by the left ventricle, right? So we know that when we look at pressure in the left ventricle, we looked at this pressure relationship. We looked at its own volume relationship, right? But we've just got the pressure relationship here. So pressure was low but rising during ventricular diastole. All right, so we're just at the end of the period of rapid filling, right? And then we get this little bump up because the atria contracted, which emptied a little bit of volume into the ventricle, so we get this little bump up in pressure. And then the ventricle started to contract, right? So we started with in ventricular systole. We started to contract. the mitral valve closed. So the valve between the atria and the ventricle closed because we're building up that pressure. And the aortic valve is not open yet, right? So the ventricle is building up pressure with no change in volume. This was that isovolumetric contraction that we talked about. Okay, so it's just a review of what we did before. And then the aortic valve opened. So at some point we exceeded the pressure in the aorta, right there. Our aortic valve opened. Oh no. Okay, so right there, the aortic valve opens. We start to eject volume into the aorta. And then the ventricle starts to, goes from systole to diastole again. So we start to relax, we stop contracting. So we stop contracting in around here somewhere. So now pressure is dropping in the ventricle. And at some point, the pressure in the ventricle goes below the pressure in the aorta. The aortic valve closes. So we get this huge drop in pressure. There'll be no change in volume in that ventricle. That's our isovolumetric relaxation. And then we go through the period of rapid filling again. Okay, so that's kind of where we've been with the ventricle side of things. Okay, and so now let's look at what was happening in the aorta during that process. Okay, in the aorta, from the previous contraction, there was volume that was put out there, right? So there is an elastic nature to the aorta. The volume was put out there, and then we get a little bit of elasticity now pushes the volume forward, right? We have a pressure drop, right? So volume is now moving from the aorta into the small arteries, resistance arterioles, capillaries, et cetera, right? So the volume we put in is leaving that compartment. So pressure is dropping, right? So we'll start with pressure dropping to, I think that we've been using 80 millimeters of mercury. All right, so the pressure is dropping. By the time it's about 80 millimeters of mercury, the heart is contracting. Okay, so the heart is contracting, the mitral valve closed, we're going through isovolumetric contraction. It's pressure is about 80 millimeters of mercury in the aorta, and then the ventricle creates 81 millimeters of mercury. The valve opens, and we start to eject volume, right? That was what the ventricle was doing. It's ejecting volume into the aorta. So aortic volume goes up, and aortic pressure goes up. Okay, so aortic pressure is going up now because we're filling it. All right, so we fill, we start to put volume into the aorta, we start to see this increase in pressure in the aorta, then the ventricle starts to relax and starts to decrease its pressure, so we do see this drop in pressure, and then the aortic valve will close, right, because pressure in the ventricle got lower than pressure in the aorta. Aortic valve closes. Right about there. And once the aortic valve closes, now the aorta has as much volume as it's going to get from that contraction, right? Because the aortic valve is closed, the ventricle can't empty any more volume into that compartment. So we get a representation here of what pressure is, of what volume and what pressure is. And then because this is the highest pressure in that tubular system, volume starts to move out, going into small arteries, arterioles, capillaries, et cetera. So as we move volume out, pressure in that compartment will drop. Okay? So there's a little bit of a weirdness here, this thing called the dichroic notch. It is like, so when you actually measure pressure, there will be this little dip in the pressure measurement, and it's thought that in order to actually get that aortic valve to close, You actually need a little bit of backflow in order for it to stop, right? So when pressure in the ventricle goes below pressure in the aorta, you'll get a little bit of backflow because that's the pressure gradient, and that's what snaps the aortic valve shut. And then once the aortic valve is shut and nothing is moving in that instant, that's when we get a real volume pressure measurement. Volume pressure measurements that are happening right around there, there's a lot of dynamics happening. Everything is moving. Volume is coming in, volume is moving out at the same time, right? So you're not really getting a true pressure-volume relationship, but the thought is when that aortic valve snaps shut, then right there, you're getting the right volume pressure relationship. So you're getting a true reading of what pressure is, and then that's our highest pressure that is now driving flow across the rest of the system, okay? So you do get a little bit of weirdness. And apparently we're done for the day. All right, we'll see you tomorrow, or we'll see you Friday.